in here to be listed together with those great people. And also, it's very nice to visit visit Florida from Buffalo during the winter time. At the day I left, we got 10 inches of snow. So don't complain, it's chilly here. It's very warm for me. All right, so I'm going to talk about our recent work on robust reinforcement learning under model uncertainty. So um, the motivation for this kind of problem is that when we train a reinforcement learning algorithm, we typically get data or build the model using a simulator or in a well-protected environment. Let's say the picture on the left is a drone flying facility at Buffalo. You can see it's a net protecting everything. It's a very clean region, and you don't really expect anything, sudden adversarial or whatever, right? So you train your drone, let's say in this environment, but probably when you really deploy your drone, you may fly the drone to complete some task near the seaside where you may expect a random gust wind from a random direction or what. So there must be a mismatch between the training and the test environment. And we call this model mismatch. And this may lead to some severe performance degradation if you don't take this into consideration during the training time. And generally, this model mismatch could be due to modeling error between the simulator and the real environment, or the environment just evolves slowly over time. It's not stationary, or you may expect some unexpected perturbation or potential adversarial attacks, like a robot is working and something. All right. And the goal here is just to find a good policy that will perform well under this model mismatch. So before I dive into robust reinforcement learning, let's just introduce some notation and some basics. So the mathematical model behind this is the Markov decision process. And we have an agent interact with the stochastic environment. At each time step, the agent observe the current state of the system, and based on the current state, the agent take an action, and then the environment transits to the next state according to a transition kernel. At the same time, the agent receive a cost C, and that's pretty much a standard Markov decision process. And commonly used the performance criterion is called the discounted value function, which is the overall cost over time multiplied by a discounted factor, right? So, and the goal is to find the optimal policy that minimizes such a value function. Okay. But for robust Markov decision process, instead of having a fixed transition kernel or fixed Markov decision process, we have a set of Markov. So we have a set of transition kernels, and this uncertainty set of transition kernels. For example, we can build it like we collect a number of samples, and we get an empirical estimate of the transition kernel. But it's from samples. So the accuracy or the confidence depends on the number of samples, right? We can build a confidence region around this empirical transition kernel and make it with high probability such that the true transition kernel falls into this answer. And we take a pessimistic approach in face of this such uncertainty. We take the worst case cost over this uncertainty set. So we define this robust value function. As you can see here, this expectation is the expected discounted cost, right? Accumulated discounted cost. And then we take the worst case. This worst case, since it's cost here, we take the max over all the transition kernels in the uncertainty set. And then the goal here is just to optimize such worst case performance. So there are quite a few works in the literature on the robust reinforcement learning. Uh, so the model-based approach basically assumes that, let's say, we know this uncertainty set exactly. It's just given to you beforehand. And people have developed a robust dynamic programming approach to solve this model-based setting. And recently, people are trying to extend this model-based setting to the model-free setting. Intuitively, we just don't know the entire uncertainty set explicit. We just have, let's say, we have a simulator, which is the centroid of the uncertainty set, or we call it a nominal transition kernel. So we get samples from the nominal transition kernel, and we know that, okay, this uncertainty set is centered at the nominal transition kernel and defined via, let's say, KL divergence, total variation, so on and so forth. And several different uncertainty set structures have been investigated in the literature. The first one is a ellipsoid structure type of uncertainty set. Basically, it's a ellipsoid centered at the nominal transition kernel. And there are also KL divergence defined uncertainty set, but the result is for the generative model, you can arbitrarily pick a state action pair and generate the subsequent state and get the associated reward. And the result is for the tabular setting. In the last 2 years, we have results on the contamination model. I will introduce the contamination model later, but we develop model-free algorithms, and we have asymptotic convergence and the sample complexity analysis, and we can combine our approach together with a function approximation. We can handle the case with large data spaces. And there are also approaches that are offline. So the idea is just to collect a number of samples, estimate the empirical transition kernel using the MLE, and then build a ball around the empirical transition. Another important setting is the average reward setting or average cost setting. So in the previous discounted setting, we need to discount the reward over time. So it's kind of, if we choose a large discount, a small discount factor, gamma smaller than 1, then the obtained policy might be myopic. It only prefers instantaneous reward over delayed reward. But for there are systems that may operate for extended range of time. Let's say a communication system, you want it to work forever, and we just want to optimize the average reward over time. And the literature on this setting, the average reward setting, robust average reward setting, is actually very, very limited. There is only one approach in the literature, but their approach is only for so it's called a bounded interval uncertainty set. Basically, they have a nominal transition kernel, let's say P, and then P plus delta minus delta is the defined uncertainty set. So the structure is kind of simple. And the approach they take is a limit method. Basically, they use a discounted approach to asymptotically approximate this average reward set. So we will dive into the details later, what is so-called the limit approach. And then recently, we have developed a general framework. So our approach applies to a wider range of uncertainty sets. And we developed the robust average cost Bellman equation. We characterize their solution structure. We develop limit method, direct method. Okay. And we also look at the model-free approach, where we don't know the uncertainty set, but we can take samples from the nominal distribution, the centroid of the uncertainty set. And our approach can still be applied to general uncertainty sets. and we developed the so-called robust relative value iteration, and we have convergence. All right. So for robust reinforcement learning, there are also quite a few heuristic approaches in the literature. For example, the first one is called adversarial state transition perturbation. It's just like a robot is working. I'm an adversary. I just pick the robot. I just change the next state of the robot. And then the agent is trained by adversarial training approach. I'm trying to optimize my attack strategy, and the robot is trying to optimize his or her own reward. The second approach is called adversarial sample perturbation. So I'm still acting like as an adversary, but I'm not really picking the robot. But I'm changing your observation, the agent's observation. So you get somehow contaminated observation. It's fake, but the robot is left unperturbed. Okay. They all work very well on various scenarios, but our aim here is trying to understand, build a theoretical framework. We try to understand what are the solutions, what are the policies we are really getting. Um, all right, so here is the robust average cost reinforcement. So we have, let's first define, record the robust let's first look at the average cost. So we take the average of the cost from time 0 to time n minus 1. We take the average and we let n go to infinity. So it's the average over time. And then we then further take the worst case over the transition kernel. Okay. And then we try to optimize the worst case performance. So it's essentially a min-max approach. And if we can exactly solve this problem, we know exactly what kind of policy we are getting. Right? We know we are getting a min-max optimal policy. We know we are optimizing the worst case performance. And then we also know that when we really deploy the policy, we have a worst case performance. And our main results include development of the so-called robust average cost Bellman equation. And we understand the properties of the solution to such equation, and then we try to solve this problem. We try to find the optimal policy by developing a limit method and a direct method. Okay, and we also have model-free approaches, including robust TD and robust QD. All right. So let's first revisit classical results in the non-robust setting. So in the non-robust setting, it has been shown that for any transition kernel P and policy pi, this convergence result holds. So the left-hand side, this Vp gamma pi means the discounted value function with discount factor gamma for policy pi and under transition kernel P. And if we multiply 1 minus gamma and then let gamma goes to 1, this will converge asymptotically to the average cost. We denote by GP pi. So from this equation, we know that, okay, this asymptotically, this equation holds, then we can use the discounted value function to approximate the average cost value function, right? We just pick a gamma that is very close to 1. That will work. But a natural question is that, will we still have the same result for the robust set? Now we are looking at this script P. So it means that we need to take the worst case over the uncertainty set. The same thing happens on the left-hand side. This script P means that the worst case discounted value function. So does this limit still hold? If this limit still holds, then we just we take a large gamma and then trying to solve this discounted robust value function, so we can solve the problem. For that part, I just quickly review the literature. people have for discounted robust value function, people have developed the robust discounted Bellman operator, which is written in this way. C is the cost, gamma discount factor, and this sigma is called the support function. Basically, if you look at this expression, it takes the worst case of the next state value. Okay, and then people shown that this T, the robust discounted Bellman operator, is actually a contraction. So that makes everything very elegant, right? If you have a contraction, then you can design you repeatedly apply this robust Bellman operator, then you get the unique fixed point. All right. So the only question left to ask is that whether this convergence holds. Now, so in the only literature for the bounded interval uncertainty set shows that that limit holds. But their approach is kind of specific to this uncertainty set structure. The thing is that they showed that the number of possible worst case transition kernels is finite. Now you see that this the worst case here taken here, the max over transition kernel here, you can equivalently write it as the worst case over a finite set. Then you can just exchange order of limit and the max, right? So everything is interchangeable. And then, however, this approach, it relies on this bounded interval uncertainty structure. So the structure, like I said, is just a p plus delta minus delta, an interval. It's quite simple. But this is not generalizable to other uncertainty sets like divergence, total variation. So to address this the asymptotic convergence, the robust version, we first show that for the non-robust case, this convergence actually is uniform. This is a uniform convergence. So with this result, with this uniform convergence, we can see that the left-hand side is the worst case average cost, right? And we plug in the definition here. This mean and the limit, because the convergence is uniform, we can just exchange the order. So this holds for any compact uncertainty set. So therefore, it's quite general. Any, the probability simplex is bounded, and those uncertainty sets defined by KL divergence, total variation, chi-squared, they are all compact. So we can show that this convergence is uniform. So then we can approximate the robust average cost using the robust discounted value function. So with this understanding, we can design the so-called the limit method. So the limit method is quite intuitive because we have that asymptotic convergence. We just repeatedly apply one-step robust discounted Bellman operator, but we keep increasing the discount factor. So then this is just the one-step robust discounted Bellman operator with discount factor gamma t. As you can see that gamma t is defined in this way. So as t increases, gamma t will approach 1. So therefore, we can expect that this approach will eventually converge to the robust average cost. That's what we show here. When t goes to infinity, this converges to the robust average cost. So this approach solves the policy evaluation problem under the robust average cost setting. And because we choose the gamma t in this way, every time you are shrinking towards the fixed point by a factor of gamma t, and you multiply gamma t over t, you can expect that the convergence rate will be 1 over t. So this is kind of slow for dynamic programming type of approach. But we will show that later we develop a direct approach which will achieve a linear convergence rate if converges exponentially fast. And of course, this approach will also work for this optimal control problem. We just replace the expectation over a policy pi by take the mean over action A. So everything is very similar, and then we can show that this V will converge to the optimal, the min-max robust average reward, and the policy derived by taking a greedy approach converge to the optimal robust policy. So next we show some simulation results. So we compare a regular vanilla value iteration with the robust value iteration. So we plot the performance of the obtained policy under the worst case transition kernel in the uncertainty set. So intuitively, we try to train using it's model based. There is no training, so we try to evaluate the worst case performance over the entire uncertainty set. And this blue curve is the non-robust value iteration, the vanilla one. This orange one is the robust value iteration. Now, this when we do this, we plot the reward. So the higher the better. So you can see that in the worst case transition kernel, we can achieve a higher reward by using the robust work. Okay. These three figures corresponding to three different uncertainty sets: contamination model, total variation defined uncertainty set, KL divergence defined. So we also have other uncertainty set like chi-square, Vessel standard. It's not listed. Yes, yes, yes. So they are product sets for different state action pairs. You can see that even if we just look at these two curves, there's a big gap. So you are talking about if we just look at the performance on the nominal transition kernel. Yeah, we lose quite a bit. Yeah, I don't have the plot here. We do lose. All right. So another result is called actually an analog to the Blackwell optimality for the non-robust setting. So in the robust setting, we also have a robust Blackwell optimality. So what is the so-called Blackwell optimality? It's describe a connection between the discounted setting and the average reward setting. What this result is saying that we suppose there exists a delta. It's a constant less than 1, such that if you pick any discount factor larger than delta, and then you try to get the optimal policy for this discount factor, for the discounted setting, this policy will also be optimal for the average cost. So intuitively, if we pick a large enough discount factor gamma, solve the discounted setting problem, you also get optimal policy for the average. Right? But the proof is quite different from the non-robust setting and that specific bounded interval uncertainty set. So just two sentences to describe the main difficulty is that the property they try to use is that this function is for two policies, pi and mu. The value function, discounted value function, is actually a rational function of gamma. Since it's a rational function, then it has finite number of zeros. But if we look at this robust version of the difference, we need to take the max over the uncertainty set. which naturally make this not a rational function. So all the nice properties are gone. We don't have that. All right. So a basic summary is that the limit method, we try to solve the average reward robust problem using robust discounted problem as intermediate step. Uh, but this doesn't review fundamental structures of the average reward problem. So that is the goal of our next session. So in the next session, we need an assumption to make the analysis simpler. We need the unit chain assumption. So for any transition kernel in the uncertainty set and the policy, any policy pi, the induced Markov chain is unit. Try to rule out the possibility that the average cost is not a constant multiplier or one vector. All right. So we first develop this robust Bellman equation. So it's analog to the Bellman equation in the non-robust setting, but here you can see that we have the sigma as we introduced before. It's the worst case expectation of the next state value function. Okay. We take the max over this uncertainty set, P transpose V. It's the expectation of V for the next state. And this robust Bellman equation, if we have a pair of solutions, so now we have two variables. Unlike the discounted setting, we have two variables. G corresponds to the average cost, and we typically refer it as a relative value function. So then if we can find a solution to this equation, then we can claim that this G is actually the optimal robust average reward. Okay. And if we further derive a policy using a greedy approach from this equation, then this pi star, this policy will be an optimal robust policy. All right. So then if we want to solve the average cost MDP, then we can just try to find a solution to this robust Bellman equation. Right. So how do we do that? So this is just a copy of the robust Bellman equation. In the discounted setting, as we commented before, we have the contraction. We just repeatedly apply the robust Bellman algorithm. But here it's not essentially a contraction, and it may have multiple fixed points, and the algorithm may or may not diverge. All right. So we try to generalize the idea of relative value iteration for the non-robust setting to the robust setting. Okay. So the same idea of using an offset function, we also use that here. We try to keep the iterate stable, and our convergence proof is also similar. So the high level idea is similar. Of course, the techniques is very different. We prove it is a multi-step contraction, then we have the convergence. All right. So let's look at the algorithm. So now we don't really use discounted setting as intermediate step anymore. We just use this, apply the robust average reward Bellman operator, subtract an offset function f. So this offset function is kind of easy to construct. Some examples include you can just pick an arbitrary reference state using v for that state as the function of fb. And we can also use, let's say, take the average of all the entries of v, using that as the reference offset function. So that all works. And we can show that this f of vt and vt, this pair, will converge to a solution to the robust or optimal robust Bellman equation. So like we said, if we find a pair of solution to the optimal robust Bellman equation, then we can solve the problem. We have the optimal robust average reward cost, and we can derive optimal policy from that. Here we can achieve linear convergence exponentially faster to the optimal policy and the optimal average cost, which is quite much more faster than the limit method, 1 over t for the limit. All right, so this is the simulation results. Again, the setting is completely the same, all the same as the previous one. We do we evaluate the worst case performance of the obtained policy. We compare the non-robust value iteration with this robust relative value. Okay, the relative. 3 different uncertainty sets, and the orange one is our robust algorithm. The blue one is the non-robust version. And again, this is for reward. So the higher the better. So we can see when we really evaluate the worst case performance of the obtained policy, this orange curve is much. Right. So all the previous slides, we assume that the uncertainty set is given to us. We don't need to take any sample. So that's we so-called model-based setting. So now we try to generalize all the algorithm to the model-free setting. So when we say model-free, we know the structure of the uncertainty set, just we don't know the explicit expression of the nominal transition. So an interpretation is that okay, this nominal transition kernel is just our simulator. We can obtain samples from the simulator. Right. So the idea is to generalize the non-robust RVI relative value iteration Q-learning algorithm to this robust set. Okay. Still, the challenge are quite similar because for robust average cost setting, we don't have a contraction for the Bellman operator, and we have multiple fixed points, and we need to construct unbiased estimator for the robust Bellman operator. Okay. If it's biased and the bias does not diminish, then there's a problem. All right. So in order to do that, we need a third result for this robust average reward Bellman equation. So the first two are the same as before. The third one is new. The third one just tells us that the solution to this robust Bellman equation has to be in this structure. So as you can see that Q appears here, it also appears here. If we think about the non-robust setting, the solution to this average cost Bellman equation is just a one-dimensional thing. So this V will be fixed, something fixed plus a C multiply all one vector. Okay. But here we don't know. That's the main challenge is because if we look at the non-robust setting, there's no support function over here, right? There's just a V function over here. And then this robust, this Bellman equation will be linear. It will be linear. But now we have this sigma. We take the worst case over the transition kernel. There's a max over the transition kernel. So everything will be nonlinear. So we cannot really use the linear equations, write out the solution space, the solution structure of this robust Bellman like we did in the non-robust setting. But we can still characterize the structure. This is still not very explicit. It's not quite clear what are those Qs for this group. But this is sufficient for the convergence proof. Because we will comment on that later. Let's look at this result. So this omega G pi is actually the set of worst case transition kernels. It may not be unique. We may have multiple transition kernels that achieve this worst case. And V p pi is defined to be the relative value function. It's just the difference between the reward we receive and the average reward. We take the sum over time. So VQ, the solution to this robust Bellman equation can be written as the relative value function for transition kernel P and the sum policy pi Q plus some constant C multiply all one vector E. Okay. All right. Uh, and we then construct the robust RVIQ learning algorithm. For now, we assume that we have unbiased estimator. We will talk about the construction later. We have an unbiased estimator H hat of Q, so that the expectation of this one is equal to the true robust average reward operator. Okay. Again, F is the offset function. Try to offset the increase of the Q table so that the iterates are stable. And the FQN again, it also serves as an estimator of the average cost G dot. Okay. So this algorithm, if we have an unbiased estimator with bounded variance, then we can show that almost surely f of qn, the offset function, will converge to the optimal robust average cost. And if we take a greedy policy with respect to the Q table, it will converge to the unoptimal robust policy. Okay. So the overall approach we take to show the convergence is we follow the Boca's stochastic approximation, that's zero. One thing we need to show is that we need to characterize the equilibrium of the associated ODE function. And we need to prove that it's globally asymptotically stable. So in order to do that, we need to know what are the solutions to this robust Bellman equation. So that's why we need this expression. All right. So next we talk about how to construct unbiased estimate of the robust Bellman operator. So we look at several uncertainty sets. The first one is the contamination model. Actually, for this model, it's kind of straightforward. So this model is like with probability 1 minus r, I will just follow the simulator, follow the nominal transition kernel. And with probability r, I will take an arbitrary distribution on in the probability system. So you can see the structure is simple because it's linear. It's linear in the simulator's transition kernel. So therefore, if linear, you can use MLE, then it's unbiased. Okay. But if we look at other uncertainty sets, we don't have a linear structure like a total variation, KL divergence. There's no linear structure. We are trying to estimate the expectation of a function of a random variable instead of a function of the expectation of random variable. So if we directly use MLE method, we have a bias test, and the bias depends on how many samples you get. It will not diminish with time. We take the idea in the literature called the multi-level Monte Carlo method to estimate the expectation of a function of a random variable. The idea is the algorithm is not that complicated. We just, although it looks very long, but not very complicated. We generate a n, which is the number of samples according to a geometric random variable. And then we take a 2 to the power of n number of samples. Okay. And then we divide the number those samples into two groups: samples with odd indices and sample with even indices. Okay. And then we calculate the empirical distribution for these two groups and the entire group and the first sample. So 4 empirical distributions. So we use those empirical distributions to build the estimated uncertainty set. Okay. And then we use this expression. So this is the support function using the empirical distribution of the first sample. And this delta n is this here is the support function using the entire data, all the data. This is the support function using the even indices samples, support function using the odd indices samples. So because this n, the number of samples, is a geometric random variable. So if we just take the expectation after some algebra, you get that it's unbiased. and the variance is also bounded. Okay, so we verify this for 5 different uncertainty sets: uh, contamination, total variation, chi-square, K-divergence, Vessel standard. So it all satisfies this unbiasedness and the bounded variance. And then we have the convergence of the robust RVI killer. So it can be applied. This approach can also be applied to the robust quantity set. All right. So here is the experiment. So these are two different uncertainty sets, chi-square and the Vessel standard. So this straight line here is the benchmark, the optimal value. We calculate using the model-based approach, the previous discussion. And this orange line with the green shaded area is the model-free approach, robust RVI learning. We can see that it over with iterations, it will converge to the theoretical optimal value. Okay. All right. Here's the summary. So we look at the robust average reward reinforcement learning, which is largely open in the literature. We developed some fundamental understanding of this problem. We developed the robust average reward cost Bellman equation. We characterize its solution structure. We developed the black veil optimality, building the connection between the robust discounted setting and the robust average reward setting. And we developed the model-based approaches, the limit method, using discounted setting as intermediate step, and the direct method trying to directly using the average reward Bellman equation design relative value iteration for the robust problem. And then we generalize those approaches to the model-free setting with the robust RVI-Q learning algorithm. So all the algorithm, we have the convergence proof and some simple numeric. That's it. Thank you. Yeah, I would say it will serve as a very good candidate for the offline part. You have a bunch of samples, and then because it's samples, it, you have confidence, certain confidence. Then you may want to get a good starting point for the online part using this kind of robust approach. You get a min-max optimal solution, so it has guaranteed the performance to use as the starting point for the online. Yeah. Yes, we do. But the I believe the generalization to a online you know, a single sample trajectory is doable. But we may need some additional assumption like ergodicity. Yeah. Yeah. No. The estimation will be unbiased. That's the whole point of this multi-level Monte Carlo method. Yeah. But that would be possible if you wait for a window for a certain amount of time, collect a window of samples. If you have a ergodicity, then you have sufficient number of samples for each state action pair within that. So you will still be able to get. Yeah. Thank you.